They're hidden away everywhere. Inside power plants, your car's radiator, the air conditioner humming outside your window, even your refrigerator. They are the absolute unsung heroes of thermal management, silently making our entire modern world possible. So, okay, let's dive into this amazing piece of engineering, the heat exchanger. It really sounds like a riddle, doesn't it? Imagine you've got a hot fluid, like your engine coolant, and then a cooler fluid, like the air blowing past it. You've got to get the heat out of the coolant and into the air. But, and this is the important part, you absolutely cannot let them mix. So how on earth do you solve that puzzle?
Look, the reality is, pretty much every process that generates power also generates waste heat. A car engine, a massive power station, even the laptop I'm looking at right now, they all get hot. And if you can't get rid of that heat efficiently, well, they just stop working. This isn't some niche problem, it's a totally universal challenge.
So how do we jump that thermal gap? Well, the answer lies in a really elegant piece of physics, a device that's engineered for one specific job, to move heat between two fluids without ever letting them touch.
Now, the technical term for this is a recuperator, and the core idea here is simple, but it's absolutely crucial. The fluids are kept physically separate. This means the heat has to go on a little journey, passing through solid walls to get from the hot side over to the cold side.
To really get a grip on how that journey works, there's this fantastic analogy. Think about it like a simple electrical circuit. The voltage, the thing that's driving the whole process, is the temperature difference between hot and cold. The current isn't electricity, but the flow of heat itself. And most importantly, the obstacle that heat has to overcome is called thermal resistance. Just like in a wire, the higher the resistance, the harder it is for that heat to flow.
And that thermal resistance we just talked about? It's not just one thing. It's more like a 5-part obstacle course. Imagine you're a little packet of heat. First, you have to push through the film of the hot fluid itself. Then, you've got to fight through any layer of gunk or fouling on the inside wall. Step 3 is crossing the actual metal wall of the exchanger. Then, you might have to navigate another layer of fouling on the cold side before finally you pass into the cold fluid film. Every single step is another hurdle.
Okay, so as you can imagine, since these things are used for everything, there's just no one-size-fits-all solution. Instead, engineers have come up with a whole family of different heat exchangers, and each one is optimized for a very specific job. Let's take a look at 2 of the heavy hitters.
First up, we have the shell and tube exchanger, and this thing is a beast. Seriously, it's the most common type you'll find in heavy industry. You have one fluid flowing through a big bundle of tubes, and the other fluid flows all around those tubes, but inside a big sealed shell. They are incredibly tough, built to last, and can handle just crazy high pressures and temperatures.
And then you've got this guy, the gasketed plate exchanger. Instead of a bunch of tubes, this design uses a stack of really thin, corrugated metal plates all pressed together. This creates a massive amount of surface area in a super tiny space, which makes it incredibly efficient at transferring heat. But that compact design comes with a totally different set of pros and cons.
So when you put them head to head, the trade-offs become really clear. The shell and tube is your go-to for anything high pressure, but it's big and it's heavy. The plate exchanger, on the other hand, gives you incredible efficiency in a nice compact package, but those gaskets mean it can't handle nearly as much pressure, and it can get clogged up more easily. It really is about picking the right tool for the job.
Right. We mentioned it earlier, but we really need to talk about the main villain of our story, fouling. This is just the gradual accumulation of junk, unwanted material, on the heat transfer surfaces. And believe me, it is the single biggest operational problem engineers have to deal with.
And don't just take my word for it. The experts warn that this is a major problem, especially in those super efficient, compact designs, because you often can't clean them mechanically. You can't just stick a brush down those tiny little passages. So when they get fouled, you're in some real trouble.
And the impact is just dramatic. A clean exchanger, it's humming along at peak performance. But as that fouling builds up, it basically acts like a layer of insulation, and that chokes off the heat transfer. So to make up for it, you have to pump your fluids harder, which costs way more energy, all while your performance just keeps getting worse. It's a lose-lose situation.
And what's really wild is just how many forms this villain can take. It can be physical stuff, like that mineral scale you get from hard water, or just plain old dirt and rust. It can be chemical, from reactions that create sludge. It can even be biological. We're talking algae and other tiny critters literally growing inside your system. It's this constant,
multifaceted battle against buildup.
So, with all these challenges, you might be wondering, why do we obsess over these details so much? Well, it's because even tiny improvements in efficiency have a massive, and I mean massive, global impact.
Okay, get this. Take a big gas turbine power plant. If you can increase the effectiveness of its regenerator, which is just a fancy type of heat exchanger, by only 1%, you boost the entire power plant's thermal efficiency by 0.5%.
Now, 0.5% sounds tiny, right? Who cares? But for a single large power plant, that tiny number translates directly into millions of dollars of fuel saved every single year. Now, scale that up across all the power plants and factories around the globe, and you're talking about absolutely monumental energy and cost savings. That's why this stuff matters.
From cooling our computers to powering our cities, heat exchangers really are the invisible workhorses of our thermal world. And that constant push for better materials, smarter designs, and new ways to defeat fouling, that's a quiet but absolutely critical frontier in engineering. So it leaves us with the question, as we push for an even more efficient world, what's going to be the next great leap in the art of moving heat?